This episode is brought to you by Brilliant. We have all dreamed of owning our own personal spaceship to fly around this world or to others, but what would it take to make that dream a reality? Whether it was the Millennium Falcon of Star Wars or the Serenity from Firefly, or the Heart of Gold and Zaphod Beeblebrox from Hitchhiker's Guide to the Galaxy, we have all dreamed of having a ship to call our own to travel from world to world, or even from time to time like with the TARDIS from Doctor Who. Sometimes as a small crew on a small ship, like the Falcon or Serenity, or Rick and Morty's garbage ship. Sometimes a small crew on a huge ship, like the Liberator from Blake 7, or the Nostalgia for Infinity from Revelation Space, and sometimes it's a huge crew on a huge ship, like a Star Destroyer or the enormous rogue trader vessels from Warhammer 40k, kilometers long and crewed by tens of thousands, but owned by one person or family. Today we're going to ask what sort of technologies we need to make it possible for a person to be able to have their own ship, whether it's a fairly wealthy individual owning their own yacht, or even just everyday Joe with his own space car. And as we will see today, there are actually some pathways for a regular individual to own a personal spaceship that might unfold, even in the next century and without a particularly revolutionary science. Now, this episode is principally interested in some hard science examples and realism, but given the topic, we will also explore some scenarios that are more on the very theoretical or even sci-fi side near the end of the episode, and have some fun with it. There are a lot of options, so sit back, grab a drink and a snack, and don't forget to hit those like and subscribe buttons. So space travel is incredibly expensive, but it's already gotten way cheaper in this century, mostly from reusable rockets, and that gives us some hope for the future, though chemical rockets are not really a good path for a future in which you have a spaceship parked in your garage. Partially that's because fuel is expensive, but that needs a few caveats. First, determining actual launch costs is always a bit tricky, but the old space shuttle used to run at a cost of about $500 million per launch. That number is debatable and controversial, but more importantly for today, it isn't mostly made up of fuel. Now, it held something like 2,000 tons of fuel, but as huge as it sounds, 2,000 tons of gasoline, for instance, is only 2.5 million liters, or about 2/3 of a million gallons. Even at modern fuel prices, that's only a few $1,000,000. We don't use gasoline in rockets, generally it's high quality kerosene or a liquid hydrogen and oxygen mix. The latter is energy intensive to make and a pain to store, but it can be made by just separating water, and the cost of that is electricity. The shuttle was a bit of a fuel hog, and the Falcon 9, for instance, usually only need about $200,000 worth of kerosene, while Falcon Heavy needs maybe $500,000. But even the shuttle was still using less than 1% of its launch cost for fuel. Though if you winced filling your car's gas tank up in 2022, consider a small personal spaceship blowing through $100,000 worth of fuel. A lot of the other costs can be tossed aside by automation and computerization though. A lot of your launch and maintenance personnel might disappear from computerization and scaling up. Reusable rockets require extreme precision to make right, and require labor-intensive inspections and repairs after each use, but that is definitely one of those things that's a good candidate for going from hyper-expensive to dirt cheap, the way a few megabytes of computer memory or GPS systems are. There are no components of a modern spaceship which are inherently expensive to manufacture or maintain. Even when we use stuff like gold for spacesuit visors or mirrors, it's not much. That enormous gold-coated mirror array on the James Webb Telescope is just under 50 grams, or 1/10 of a pound, a couple $1,000 worth of gold based on the price as I write this in August of 2022. High-quality aluminum for the spaceship frame is also one of those things that more advanced manufacturing and cheaper electricity make much less expensive. Truth be told, we really are not that far from being able to economically mass print parts. And of course, the nature of printing or a self-replicating economy is one where a lot of your gear for making your feedstock and power supply is also suddenly cheaper too. potentially causing a plummet in price tags for things like engines, super precisely machined airframe or rocket nozzles, and so on. So we could imagine a civilization where people did own rocket ships that could blast them into orbit every day. One where most or a large fraction of the cost was fuel, as it tends to be for cars, and where that amount of fuel was a bit smaller and much cheaper, maybe tens of thousands or so dollars per launch. That's definitely not personal car type space travel, but it is one where the cost to fly to space for a vacation or business trip starts getting comparable to chartering a personal jet or maybe even a first class international flight. Also, on an alien world rich in methane, for instance, that we colonized, the cost of fuel is just pumping it really, and a few thousand colonists might pump it as casually as we do water for farming. And that presumably requires a pilot, though in reality a machine mind weighing a few kilos and capable of lightning-fast reflexes and incapable of being distracted, sleepy, or malicious might be a preferred option. Now, in the shorter term, this is probably an example of human-machine teaming, where your autopilot is designed to augment the human pilots and serve as a backup, and people might prefer that. Such being the case, you could run your own spaceship to and from orbit, ferrying a dozen passengers on each leg, and probably be able to make more than one trip a day. In the same sort of economy, we also have the option for someone to own the equivalent of an interplanetary freighter, what we call a cycler or space castle. The notion there is to put a big heavy craft on a long elliptical orbit, crossing the orbit of two planets, usually Earth being one, but it doesn't have to be and could also be an asteroid or Lagrange point, and these don't stop, they just swing past those worlds. They require no refueling, same as anything else orbiting, maybe a few nudges here or there. What that means is that a small and light ship meant for darting to orbit and back down to the ground that's led on things like comforts and radiation shielding, since it has to pay the fuel bill for them each time, can instead dock with one of those slow behemoths for the long jaunt to another world, which can afford way more armor and amenities. Cycler castles are an example of a big ship that doesn't really need much crew, but might have a lot too. Hospitality services for passenger and maintenance crews for spaceships. Indeed, they might have large hydroponic facilities for growing food and recycling air and water. Plus, they would be far easier targets for automated fuel pods to be sent to, given that they don't deviate from their predicted course much and could easily open a pod launch from some fuel depot or refinery, where they could then refuel smaller ships, or receive spare parts too. Now, cyclers are slow, and interplanetary ones have trip times comparable to the orbital periods of the planets they service, which means they aren't so much hotels as short-term homes where you'll be for months or even a couple years, though they also work for orbits around planets, not just stars, so you could see these on trips between orbital colonies or multi-moon systems where the duration of trips are weeks or even days. Spaceships might be used to launch assist like mass drivers too, and radiation tends to be high in the space around such worlds, so a big cycler with thick shielding might be handy. If you own a personal spaceship docked on one, it might be like an RV camp, and for the captain of an interplanetary cycler, it's less like running a hotel than being a landlord, or a freighter captain on one of those huge slow container ships we have. Speaking of moon systems around gas giants or moving around asteroid belts or collections of orbital colonies, travel is easier. Here there's no real need for any advanced or expensive spaceship. A lot of times there will be minimal escape velocities to leave these objects and move through that volume of space, and none of it is through thick air exerting extreme heat and pressure on your ship. Generally speaking, you only need the majority of your ship to be fueled by mass when you need a delta V greater than the exhaust velocity that fuel or propellant has when burning out the back of the ship. How fast all the burned or exhausted particles are moving is the exhaust velocity, and for rocket fuels that tends to be anywhere from 2 to 5 kilometers per second. The rocket equation is quite harsh when you're trying to get a ship moving at a speed similar to that exhaust velocity, and utterly tyrannical when it comes to speeds in excess of that, which unfortunately all the speeds usually need to get away from Earth, but not from moons or asteroids. A 1-ton ship trying to reach its own exhaust velocity needs 1.72 tons of propellant for the job, ideally, but to get to half that speed, it needs only a third of that fuel, 0.65 tons, and a quarter of that speed, which might be a kilometer per second, only 0.28 tons. For double that speed, 6.39 tons of propellant, and for triple, 19.1 tons. or 95% of the initial mass as propellant rather than ship and cargo. That's essentially the key problem with chemical rockets. Earth's escape velocity is more than 20 times what it is for the largest known asteroid, Ceres, which we often classify as a dwarf planet like Pluto. The higher the exhaust velocity of your propellant, the better, and the same for specific impulse, which can be thought of as how many seconds a given propellant lets you hover a rocket in Earth's gravity. Simply having the highest exhaust velocity does not automatically make something the best fuel or propellant, but it's a central feature, and to highlight that, a 1-ton ship seeking to get away from Ceres using liquid hydrogen and oxygen with an effective exhaust velocity of 4,500 meters per second is only needing about an eighth of a ton of that fuel, a lot like a car's gas tank, and that same rocket trying to escape from Earth would need 10.5 tons of that fuel, and more like 80 tons for many of the fuels with about half that exhaust velocity. That is a very simplified view of rockets, and it generally takes a lot more fuel because of the air drag too. See our Upward Bound series for more on that, but it's also important to note that at a core level, temperature is the random motion of particles. Faster particles, higher temperatures, and the higher your exhaust velocity, the rougher it is on your ship's rocket nozzles and other equipment. And that damage tends to rise sharply with temperature and pressure. For that and other reasons, it also takes far less precision manufacturing and careful maintenance to keep together a spaceship designed for traveling from one small airless moon to another, or between two O'Neill cylinders sharing a similar orbit. Personal spaceships are no problem here, even with modern technology and costs, and given the difficulty of making those places with those modern costs, it can be assumed it would be even easier to own a personal spaceship if such moon bases or rotating habitats existed. For personal spaceships on Earth though, the really big deal is heat. The rocket fuel in an energy-abundant economy might be made carbon neutral and cheap as water, indeed we might make it out of water, but if you're burning through 100 tons of kerosene to get to space for an afternoon, you still just released a few trillion joules of heat into the atmosphere. And if we had a few 100 million folks doing that a day, then you're adding a billion trillion joules of heat to Earth every day, 10 to the 21st joules, and that's about a tenth of what hits Earth every day from the sun. So it is a lot of energy, and it is going to raise the planet's temperature, though we're not talking about an oven-roasted planet here. Still, we were assuming a fairly modest fuel expenditure per personal spaceship there, and only a few 100 million people using one daily. So a chemical rocket future is one where folks on Earth could have their own spaceplane for flying around, but it's definitely a luxury here. You wouldn't want everyone to do it daily, though for folks living in orbital colonies or asteroids and moons, it's just fine. The analogy would be a bit like owning a car in a major metropolis, something of a luxury to own on a planet but not in space, but probably even that would be conservative. The other issue though is if you want your neighbor flying a plane full of 100 tons of rocket fuel or storing that at their house, or if you want anybody moving a supersonic spaceplane anywhere near human habitation, both for the sonic booms and that such vessels carry fuels and move at speeds that make them as dangerous as our biggest non-atomic bombs. As you move into other and better technologies, those problems will remain an issue for us to address. Now, I would be very dubious about folks ever letting nuclear-powered spaceships on Earth, let alone personal spaceplanes running on them, but they do way better as an option from an engineering standpoint. See our episode The Nuclear Option for a full discussion of those engines, including surprisingly safe nuclear thermal rocket models for ground-to-orbit launch. A nuclear-electric engine with a slow but efficient ion drive might push particles out the back at 10 times the exhaust velocity of chemical rockets or more. This potentially provides a very economical private spaceship for any region where folks were okay with its use, like upper orbital colonies perhaps or in the belt. An atomic rocket is obviously a scary notion, but keep in mind that the whole ship is lethal simply by being a spaceship. As we say on this show, there is no such thing as an unarmed spaceship, because some ship moving at 10 kilometers a second is carrying more kinetic energy in it than an equal amount of high explosives. Atomic rockets operating off-world can also make sure they always point their exhaust away from any nearby planet or station, and said exhaust will leave the solar system forever if it's higher than the solar escape velocity. which depending on where you are can often be as slow as 16 kilometers per second. Plus, the whole solar system is already saturated in radiation anyway, so that exhaust isn't a big deal, and a few kilograms of vaporized radioactive particles scattering across Earth on the occasional rare accident is trivial. Nonetheless, you might want safeguards to make sure those engines were pointed safely away, and might require they not ignite them until they got to a medium or high orbit, to make sure such incidents were very rare, even if you had a lot of ships using them regularly. Fears of what the fuel of a ship, atomic or mundane, can do if misused by malice or accident are likely to be a big factor in whether or not personal spaceships are allowed, or either banned or regulated into near impossibility. This is where we get to the best plausible on-planet spaceplane, at least for settled planets, as opposed to some lightly populated colony somewhere, and here we can't remove that kinetic energy, but we can remove the fuel. Our fastest jet designs utilize an engine known as a scramjet, and these and the lower speed ramjet both are often called stovepipes because of how insanely simple their function is. Air comes in the front, and we burn insane amounts of fuel to superheat it and toss it out the back. That's it. The geometry and metallurgy of the ram or scramjet is important, but there's no moving parts to the engine itself, unless you count the fuel being sprayed in and ignited. So since they have no mechanically moving parts, they might be considered a solid-state engine, which can last a lot longer and require much less maintenance than one with mechanically moving parts. However, we can replace that with an external power source by either locking on a laser beam or microwave beam, which tracks those engines and just pours energy in. If the beam goes off, the plane simply drifts slow over time, and with that kind of velocity, it's got no problem making an unpowered landing anywhere. Plus, it might be carrying a smaller and more conventional engine for getting up to a decent speed. As the beam is coming in from elsewhere and the vehicle is air-breathing, it circumvents the rocket equation, and the very nature of that device means that such a plane is constantly monitored, and given that it's an ultra-powerful laser or microwave on the vessel with pinpoint tracking, blowing up a ship that suddenly turns kamikaze is a fairly trivial exercise. The concern then becomes fire control and who is allowed to say fire and when. Such a spaceplane could get up to an orbital velocity or a large fraction of it, then either make use of a skyhook network or onboard rockets to finish the job, and now you're firing off superhot gas in the high upper atmosphere at a perpendicular angle to the ground, not down at it, so it's not really heating the world much. In a war that's more confident about nuclear safety, it might have a reactor on board and an ion drive to let it become an interplanetary ship at that point, after docking to a space station for some refueling and changing of fuel types. A space plane like this can fit in a garage too. It might have a gas engine and V2L setup for takeoff and backup, but I think it could be all electric even then, especially with good enough batteries or power transmission. You roll out of your garage or open the top and take off vertically, climb up and get locked on like a cell tower, roll out at whatever the local speed limit is for a given place and altitude. Now, once up in space, we continue this power beaming trick if we want. At interplanetary speeds, it is nice to have a propellant like hydrogen you can superheat via beamed energy from orbital stations, but you could also have a small sail that those beams could push on instead, and while that's very inefficient at interplanetary speeds compared to superheating hydrogen gas with that energy, it's quite efficient for interstellar speeds. See our episodes on beam-powered spaceships and space planes for more discussion of this topic. And based on known science, I think this is the most plausible route to personalized space travel, especially given that intense tracking is vital to allowing spacecraft to fly around the sky by the million. Other options include tether trains to orbital rings from most towns and spaceship docks on those orbital rings, like boats at a marina. That would probably optimistically still require an hour or two to get to the local tether ground station, up that tether on a tram line, and then over to your dock. That makes it more like a marina or airport where you keep your plane in the hangar. Note that in all of these cases, there's still an option for a private spaceship, even in less optimal scenarios. It's just that, in one of those options, everybody owns one and uses it as they want, and in the other, it's more likely you're either privately wealthy or you're running a commercial operation, You've got a nuclear engine on your 747-sized spaceship, and you are heavily screened and licensed for that, and you operate a service, ferrying 100 people to orbit every day, and those tickets weren't bought for the price of a cup of coffee, but they weren't like getting a second mortgage out either. That ship is a multi-million-dollar affair, and you're probably plowing 90% or more of your revenue right back into debt service, licensing cost, crew wages, land usage, noise pollution fees, fuel or energy bills, maintenance, and so on. In the following example I'll give, John runs a ship straight from New York City to Olympus Mons on Mars. The ship weighs 1,000 tons and has 100 cabins suitable for a person or for a couple who like each other enough not to mind being crowded. The accommodations are mostly in virtual reality, but there's a gym and a cafeteria and some other amenities, and half a dozen staff who are a constant challenge to scrape together payroll for. It collects its passengers in the harbor and gets beam-powered turbines to push it out to sea and up into the air. It uses a lot of that energy to grab water and electrolyze it into hydrogen and oxygen as it goes, or tanks up before going, maybe filling up on both to burn them, or maybe just hydrogen for heating via beamed energy. Then, when safely away from the city, it races up on beam-powered scramjets, then switches to beam-heated hydrogen or hydrogen-oxygen rockets to get into orbit. It isn't going to dock with anyone, rather it's going to expand out its cabin to form a ring, which it will begin spinning for artificial spin gravity. And on that ring, it's going to stretch a reflective sail for a laser to bounce off of, or a microwave mesh to absorb energy for running an ion drive. Pods of hydrogen can be fired off from the moon by a mass driver to match speed with John's ship and other ships for a price. After all that hydrogen gets trucked in from Jupiter, the ship accelerates at a fraction of a G for a day to reaching a cruising speed of a couple hundred kilometers per second, and arrives at Mars a couple weeks later, and then catches pods from Mars to give it the propellant it needs to land comfortably in the thin Martian atmosphere. John's ship could carry that slow-down fuel and maybe does, but he can carry more cargo by having it shot to him en route. There are nearly 100,000 square kilometers of orbital solar array that's auctioning its power off to the beaming grid to run that ship when it's being shoved up to cruising speed, and needs a terawatt of power, but that's not much more than tinfoil thick. John always thinks to himself the real money isn't in captaining a ship, but in owning solar farms in space, but he would never give up flying. The excitement, the new places and people, the knowledge that at any moment Earth control might flip on his autopilot, or blow him out of the sky if he doesn't work with precision. Definitely an interesting picture. Now, beamed energy is awesome but also relies on others. It generally matches fission or fusion for interplanetary work. At the interstellar scale, it is better, and you need something like cheap and safe antimatter, which is something of an oxymoron by current science, or a micro black hole, which ironically is way safer than it sounds, based on current science. See our episodes on black hole ships or antimatter factories for more discussion of those. Neither of those is very sci-fi for all they sounded, but speaking of that, what sort of hypothetical options do we have? We did an entire episode on hypothetical space drives some years back, and probably need to refresh that, but let's contemplate some different technologies instead. Now, mass is a strange thing in physics. It has the effect of both determining how strong gravity pulls on something, how strongly something is pulled on by gravity, and how a given piece of mass responds to being shoved on in terms of its new speed and momentum. This feature we call inertial mass, and we have some reason to think it might be possible to alter it. A ship's momentum is the product of its mass times its velocity, but that's its inertial mass, so a ship that started off massing 1,000 tons and moving at a kilometer per second, then flipped on its inertial changer and suddenly had an inertial mass of just 1 ton, would still have that same momentum and suddenly be moving 1,000 times faster, 1,000 kilometers per second. If this was done uniformly, it might avoid killing everyone on board at the sudden acceleration. This is definitely what we call a clock tech, technology so advanced they are indistinguishable from magic, and to which we have no clear technological pathway to, but it is in the realm of plausible science. I wouldn't hold my breath for this technology anytime soon, or honestly ever, but much like power beaming, it offers an option for the sorts of spaceship and use that we see in sci-fi. A ship whose inertial mass is suppressed has less kinetic energy than when moving at that speed should have. so it ramming into buildings shouldn't do as much damage, and your classic Neo Lightspeed ship isn't ramming into buildings and destroying them, it's ramming into planets and leaving mushroom clouds and craters. The energy conservation in inertial suppression is rather tricky. Kinetic energy goes with mass and the square of velocity, so a ship that just had its inertial mass dropped by a factor of 10 should have its kinetic energy drop by a factor of 10 from the mass, then go up by 10 squared from the sudden jump in velocity to conserve momentum. But 100 divided by 10 is 10, not 1, so its kinetic energy just went up 10-fold, which presumably violates conservation of energy unless you have some place to grab that energy from. Additionally, you can't really ignore the effect such a drop has on chemistry. As we said earlier, temperature and heat are essentially random kinetic energy of particles, so if your blood suddenly has its inertial mass drop by 10 and its kinetic energy go up by 10, then you suddenly have 10 times as much heat in your bloodstream. Obviously a pretty potent weapon if it worked that way, but there might be workarounds. It is an awesome sci-fi handwave for any authors or game designers interested in making ships easier though, because it would massively cut down on how much fuel you needed and how much damage a spaceship would do if ramming something, though you would probably have to say it was a bubble of low inertial mass, inside which everything behaved the same. Hypothetically, any particle with zero rest mass automatically moves at light speed, so an inertial drive able to temporarily drop that mass to virtually nothing, or even flat out nothing, would move at light speed. Hypothetically, if you could take that further to make it negative inertial mass, it might move superluminally, though that had bad consequences for the ship that tried it in the novel Redemption arc by Alastair Reynolds, one of my personal favorites. See our FTL series for more discussion of those kind of options, but a point I like to remind folks of is that it takes insane amounts of energy to move things at near light speed, and that rises as you get ever closer, and there's no real reason why that would stop rising going into FTL, though exceptions like the warp drive contemplate the necessary use of negative energy, and we also might imagine ships able to dump energy or fuel into pocket universes or similar too. You don't pay the fuel bill because it's all stored in some universe in which you have a tiny wormhole to, or hammer space, which isn't counted against your ship's mass. That might be actual fuel from this universe, or a connection to some younger or more compact universe that's still as hot as a star, and an in-universe wormhole to the center of a star as your rocket might work well too. Very nice power plant or weapon system for your ship as well. When it comes to options for using less energy, another one of course is microsizing. It is very easy to have your own personal spaceship if you're an uploaded consciousness who can fit on something the size of a smartphone. That doesn't mean your ship is that size though. Damage to ships from hitting stuff is all about speed of impact, and resistance to that damage is just a matter of thickness. A modest ship whose crew are human might need a meter of metal on their ship's prow, but so does a juggernaut carrying millions, and a tiny little hard drive carrying maybe millions of digital minds. Size helps in space travel, but costs more fuel, so a big lead sphere the size of a minivan plowing through space with digital mines inside is still a lot more energy efficient than some Star Destroyer-sized ship with 100,000 mortal crew. Miniaturization of a lot of drive components wouldn't work either, though one it would work for is a black hole drive, in terms of size anyway. Assuming you can keep feeding it matter, a black hole in the hundreds of kilotons range is practically ideal for running an interstellar spaceship, but it has to be a big one. 100 kilotons is what a Nimitz-class aircraft carrier masses. Black hole-powered ships are likely to weigh low megatons as a result. And you can add more black holes to ramp up power, but you can't really change black hole mass much. The smaller they are, the more power they produce, burning very quickly. A megaton black hole masses 100 times what a 10 kiloton black hole does, but lives a million times longer, about 1500 years, while pushing out 356 trillion watts of power. But the other, smaller black hole would produce 10,000 times more power. That's around 20 times the power consumption of the entire human race right now, for the bigger, lower power black hole. About 20 times all of the instant light on Earth for the smaller black hole, which would barely survive 12 hours. It's important to think on that when you're contemplating stuff, trade and cost and so on. What a ship is bringing for trade to be paying for such titanic engines needs to be contemplated in terms of all those ports of call probably having the exact same type of power plant. You are not moving food from planet to planet because they can pay for all the lighting and environmental tailoring using a power plant like that. Luxury foods might be different, of course. And as unrealistic as something like an inertia drive or light-speed drive might be, in many ways, it's the economies of sci-fi empires that make even less sense. No place where anyone can afford to own a spaceship they haul ice towards for water with is ever going to have shortages of air and drinking water, for instance. You might own some big 5 megaton trading ship kilometers long running on a megaton black hole in its basement with a crew of 100,000, but something using that same power plant could be powering the entire modern economy several times over, or lighting up around 1,000 full-size O'Neill habitats, each home to hundreds of thousands of people too. In that regard, a lot of your ships are going to be interplanetary and slower, probably keeping to a speed roughly on the same order of magnitude as the fastest exhaust velocity they can make happen by pouring energy into hydrogen. Hydrogen is ultra plentiful and dirt cheap in a space economy, and you just get better thrust by putting your energy into those than shining out the back as a flashlight, assuming you are not aiming to move much faster than you can heat that gas up to. Light has an exhaust velocity of light speed, so it always does best kilogram for kilogram as a propellant. If they can blow them out the back of the ship at millions of kilometers per hour, then figure on your typical passenger ship making that speed, and a freighter doing maybe a half to tenth. Big does not mean slow where ships are concerned, more like the other way around, bigger can be faster, but bulky and non-perishable cargo doesn't need to move fast, and if you can deliver it for less cost, that's what you do. If someone has a contract to deliver 10 quadrillion tons of ice to Mars over the next century, there's no reason to rush delivery to weeks when months are vastly cheaper, while at the same time you have operating costs for owning that ship, so you don't want to go too slow either. In one direction, these become space cars or maybe RVs or yachts. They really are not going to be junkers like the Millennium Falcon is often shown to be. Maybe in a period of strife or techno-barbarianism, after a war you might have clunkers, especially around multi-moon gas giant systems or asteroid belts. But otherwise, it's an energy-abundant economy that's probably got robot vacuums and mops better than what we have now, so the ship is not dirty. Keeping that in mind, the other direction for ships to develop in is big ones. Those might still be small crewed or single too. Automation can do amazing things. Big crews on big ships also might still have tons of elbow room. Some kilometer-long ship with a crew of 10,000 might sound crowded like a submarine, but in practice, that thing would have vastly more room than even our biggest skyscrapers, and there's quite a few thousand of those with thousands of residents and often shopping centers and community areas too. So whether your megaship has a crew of 10,000 or 10, there's a lot of room for things like hydroponic bays, but also for gardens, tennis courts, swimming pools, a ship's water reserves might as well be in a pool or aquarium after all, and a ton of other features. Also, all those big habitats we talk about, like O'Neill cylinders, if artificially lit, can essentially choose to be spaceships too. You might have your own interstellar ark ship and nature preserve containing 10,000 acres of forest, for instance. For that matter, a large habitation drum of many hundreds of acres might be the living quarters for a mega freighter pushing ice that could fit something like that in its proverbial closet. Assuming we survive the next few decades and technology progresses to better automation and energy abundance, and we cross into a post-scarcity civilization, that is a future where your own personal space car or your own personal space habitat even become real possibilities. Needless to say, there are a lot of unknowns and unknown unknowns that limit our ability to discuss this matter, but what we do know tells us there's a good chance people in the future might be able to own their very own spaceship. One thing about having your own spaceship is you have to be able to navigate the thing, and that's an area where knowing your geometry and trigonometry can really help, even when you have computer assistance. The notion of trying to calculate an atmospheric entry probably seems a bit intimidating, but it does not have to be. and a powerful knowledge of trigonometry and geometry is helpful in so many areas of life. That's where Brilliant's mini interactive courses on geometry can help. Many topics in math and science can seem hard because there's no interactive and intuitive way to work with the idea, compared to more traditionally hands-on topics that you can play with and thus learn easier. So Brilliant focuses on making interactive and hands-on content, which makes it easier for anyone to learn, be it basic math or advanced topics like probability simulations. Folks often ask how higher math will help them in day-to-day life, but believe me, once you know it, you'll see real-world practical cases to use it everywhere you look. A better knowledge of math, science, and computer science can not only be enlightening personally, but a road to greater personal success. Be a lifelong learner, and let Brilliant be your partner on that journey. With Brilliant, you can learn at your own pace, learn on the go, and learn something new. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. I'm never sure how much attention folks pay to the intro overlays or credits, but this is the official episode 365, which now means you could watch this channel every day for a year and not repeat an episode. Though in point of fact, the official spreadsheet of episodes lists this as entry 490, since our live streams, collabs, Sci-Fi Sundays, and other bonus episodes are not counted in our official weekly chronology of episodes, nor our Nebula or audio-only exclusives. If you're curious, we have a publicly viewable list of every episode on YouTube we've done, which I'll link in the episode's description. Folks are often surprised that when they ask for a topic, it's one we've already done before, sometimes even twice, since we tend to revisit certain topics for updates and extensions. It is also where you can see our full list of planned and finished episodes, which is usually about 3 months ahead, not just the month or so I usually put up at the end of episodes. Speaking of next month's schedule, we still have one more regular episode, 366, coming up this month, where we'll continue today's discussion by asking about what to do if your spacecraft gets damaged or you get shipwrecked. Then we will close out the month on Halloween weekend with our live stream Q&A on Sunday, October 30th at 4 p.m. Eastern Time. Join us live to get your questions in the chat so they can be answered. After that, we'll head in November to discuss refueling the Sun, an option that could make it possible for us to keep Earth going for trillions of years to come. And then come back more to the present and near future to discuss what an automated economy would really look like, how it would take shape, and the possible problems of unemployment. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website isaacarthur.net for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.